Section 2.3, The Modern View of Atomic Structure. Since Rutherford's time, as physicists have learned more and more about atomic nuclei, the list of particles that make up nuclei has grown and continues to increase. As chemists, however, we can take a simple view of the atom because only three subatomic particles, the proton, neutron, and electron, have any bearing on chemical behavior. As noted earlier, the charge of the electron is negative 1.602 times 10 to the negative 19 coulombs. That of a proton is equal in magnitude, positive 1.602 times 10 to the negative 19 coulombs. The quantity 1.602 times 10 to the negative 19 coulombs is called the electronic charge. For convenience, the charges of atomic and subatomic particles are usually expressed as multiples of this charge rather than in coulombs. Thus, the charge of the electron is negative 1, and that of the proton is positive 1. Neutrons are electrically neutral, which is how they receive their name. Every atom has an equal number of electrons and protons, so the atoms have no net electric charge. Protons and neutrons reside in the tiny nucleus of the atom. The vast majority of the atom's volume is the space in which the electrons reside. The electrons are attracted to the protons in the nucleus by the electrostatic force that exists between particles of opposite electrical charge. In later chapters, we'll see that the strength of attractive forces between electrons and nuclei can be used to explain many of the differences among different elements. Figure 2.11. The structure of the atom. A cloud of rapidly moving electrons occupies most of the volume of the atom. The nucleus occupies a tiny region at the center of the atom and is composed of the protons and neutrons. The nucleus contains virtually all the mass of the atom. Atoms have extremely small masses. The mass of the heaviest known atom, for example, is approximately 4 times 10 to the negative 22 grams. Because it would be cumbersome to express such small masses in grams, we use atomic mass unit, or AMU, where 1 AMU is 1.66054 times 10 to the negative 24 grams. A proton has a mass of 1.0073 AMU, a neutron 1.0087 AMU, and the mass an electron 5.486 times 10 to the negative 4 AMU. Because it takes 1,836 electrons to equal the mass of one proton or one neutron, the nucleus contains most of the mass of the atom. Most atoms have diameters between 1 times 10 to the negative 10 meters and 5 times 10 to the negative 10 meters. A convenient non-SI unit of length for atomic dimensions is the angstrom, where 1 angstrom is 1 times 10 to the negative 10 meters. Thus, atoms have a diameter of approximately 1 to 5 angstroms. The diameter of a chlorine atom, for example, is 200 picometers, or 2 angstroms. The diameter of an atomic nucleus is approximately 10 to negative 4 angstroms, only a small fraction of the diameter of the atom as a whole. You can appreciate the relative size of the atom in the nucleus by imagining that if a hydrogen atom was as large as a football stadium, the nucleus would be the size of a small marble. Because the tiny nucleus carries most of the mass of the atom and such a small volume, it has an incredibly high density, on the order of 10 to the 13th or 10 to the 14th gram per centimeter cubed. A matchbox full of material of such density would weigh over 2.5 billion tons. An illustration of the atom that incorporates the features we've just described is shown in Figure 2.11. The electrons play a major role in chemical reactions. The significance of representing the region containing the electrons as an indistinct cloud will become clear later chapters when we consider the energies and spatial arrangements of the electrons. Atomic numbers, mass numbers, and isotopes. What makes an atom of one element different from an atom of another element is that the atoms of each element have characteristic number of protons. Indeed, the number of protons in an atom of any particular element is called that element's atomic number. Because an atom has no electric charge, the number of electrons it contains must be equal to the number of protons. All atoms of carbon, for example, have 6 protons and 6 electrons, whereas all atoms of oxygen have 8 protons and 8 electrons. Thus, carbon has an atomic number of 6, and oxygen has an atomic number 8. The atomic number of each element is listed with its name and symbol of the element on the inside front cover of the text. Atoms of a given element can differ in the number of neutrons they contain and consequently in mass. For example, most atoms of carbon have 6 neutrons, although some have more and some have less. The symbol carbon 12 represents the carbon atom representing 6 protons and 6 neutrons. The atomic number is shown by the subscript. The superscript, called the mass number, is the number of protons plus neutrons in the atom. C is the carbon symbol of the element. 6 is the atomic number, which is the number of protons or electrons. And 12 is the mass number, or the number of protons plus neutrons. Because all the atoms of a given element have the same atomic number, the subscript is redundant and is often omitted. Thus, the symbol for carbon 12 can be represented as simply C sub 12. As one more example of this notation, carbon atoms that contain 6 protons and 8 neutrons have mass number 14, are represented by carbon 14, referred to as carbon 14. Atoms with identical atomic numbers but different atomic mass numbers, that is, the same number of protons but different numbers of neutrons, are called isotopes of one another. Several isotopes of carbon are listed in Table 2.2. We will generally use the notation with superscripts only when referring to a particular isotope of an element. Some isotopes of carbon. Carbon's isotopes include carbon 11, carbon 12, carbon 13, and carbon 14.